So let me just start by reminding you what I said yesterday. I said yesterday that given some, given AdS CFT, you put it at finite temperature. There's a dual state, which is that of a black hole, and then at finite temperature also you have these generalized free fields in AdS CFT. These generalized free fields are the usual kind of operators we often talk about, like the stress tensor or like trace of f squared. And these operators, these conformal primary operators, are dual to some fields in the bulk. And you can write down a mapping between these boundary fields and a local bulk operator. Okay. So yesterday I wrote down this formula for this local bulk operator, which roughly said that you want to write down some local bulk operator at some radial point z and some position x and some time t, and you can think of it as this boundary mode normalized in some particular way divided by this commutator and multiplied by some solution of the wave equation. And yesterday I described how you would have to normalize the solution of the wave equation as well. Okay. Okay. We wrote down this formula yesterday, and this formula is valid outside the black hole. Then I said, now we want to extend this inside the black hole. Okay. And if you want to extend this inside the black hole, I ended in talking about Rindler space yesterday when I said, if you think about Rindler space, then Rindler space, has these regions 1, 2, 3, and 4, and you can, you have some expansion of modes in region 1, and then if you go into, region 2, as you heard today from Gautam also, you have some modes here which we call E omega, and you have some modes here which we call A omega and B omega, and if you wanted to go from, if you wanted smooth 2-point functions between region 1 and region 2, then you needed to have, that this was this, and the behavior of these B omegas on states was that BW on the state psi, whatever the state of the field is, was equal to e to the minus. Okay. So we had to have this relation between, first these operators just by continuity, and then the action of BW on these states. Okay. Now, as you know very well, if you don't know very well, take this as a statement. The semi-classical expectation is that a black hole, if you think of a big black hole, okay, the horizon locally looks like Rindler space. Okay. So these Schwarzschild coordinates that you set up outside the black hole are the analog of the Rindler coordinates. Okay. And the Kruskal coordinates, what one calls the Kruskal coordinates, okay, are the analog of the Minkowski coordinates. Okay. So locally, the Bogoliubov transforms that you write down, which you've been hearing about yesterday and today, between the Rindler modes and the Kruskal modes are the same. Sorry, between the Schwarzschild modes and the Kruskal modes are the same as these transforms, between the Rindler modes and between, the Minkowski modes. Okay. So the claim is that if you wanted to write down an analogous formula inside the black hole, then you would have to, by analogy with Rindler, you would have to write down. So when I write zxt, this zxt can I can introduce another Schwarzschild patch in this region 2 as well. Okay. So I drew this diagram for Minkowski and for for Rindler, but I might just as well think about a black hole in AdS, which has the following diagram, and again has let me talk about a collapsing geometry. So you create some geometry by collapse. Okay, let me just describe it in some more detail for those of you. So this is AdS, and you create you insert some matter, insert some energy. This energy from the boundary goes and collapses to form a black hole. So this shaded region is is this matter that you inserted. This is the horizon. Okay, and you want to describe physics in some point here, okay, which is far away from the matter, and it's somewhere behind the horizon. Okay, do you want me to draw bigger for those of you at the back, or can you see this point P? Okay, this is the point P. Arrow is. If you like, I can enlarge this portion. Yeah. So this is the matter. This is the matter. Okay, and I want to discuss a point here, which is. I want to discuss a point here, P, which is far away from the matter, but it's behind the horizon. Okay. Okay, so I'm just enlarging this portion. There's some matter. The matter has some surface. It's falling into the black hole. This is the horizon, and I want to discuss, this point P here. Okay. Now the claim is that locally, and this is something that is again, I mean, it's a GR fact, is that locally, this setup of this point P and this region here looks a lot like Rindler space. Okay, it looks like the region 1. This region is like region 1 of Rindler space, and this region where this point P lives is like region 2 of Rindler space. Okay. Of course, if you try and go very deep into region 2, then it's different, because at some point you hit the infalling matter. Okay. And also, if you have a small black hole, then things are different, because then curvatures might be large at the horizon. But if you take a big enough black hole, then the horizon is basically a smooth place. The horizon is very much like flat space, and so this boundary between region 1 and region 2 of the black hole is the same as the boundary between region 1 and region 2 of Rindler space. Okay. I'm actually assuming that you've seen this before, so I'm trying to go through this a little fast. But if that assumption is incorrect, please stop, and I'm happy to answer questions about this fact. Okay. This fact that the horizon of a black hole is locally like, looks like, or the black hole locally looks like Rindler. This is something if you haven't seen before and you have questions about, please feel free to stop me and we can discuss this now. So right now I haven't, what is this ZXT? This F hat? This F hat is the mode I discussed yesterday, which was a solution to the wave equation which had a particular normalization. It was a solution to the wave equation which went like a plane wave and went like a momentum plane wave in X, and it was one of the solutions to the radial equation which I picked by demanding normalizability at infinity and demanding that it had plane wave behavior in the tortoise coordinates near the horizon. That's this F hat. So I defined this yesterday. So the situation is that you think of a setup like this where you insert some matter from the horizon, it goes and collapses into a black hole. At this level, there's nothing different between AdS and between flat space. So I'm blowing up this part of the diagram here. Okay. So here's some matter which is going and collapsing. It's going to go and collapse into a singularity at some point. This is the horizon that's formed. This is the null ray, which is the horizon. I want to discuss a point P which is behind the horizon, but which is far away from the matter, which is also far away from the singularity. So it's a point P in a region of weak curvature if it's a big enough black hole. Okay, and the claim is that if you think of these two regions, the region outside and the region inside the horizon, and you think about this in Schwarzschild coordinates that you set up here and you set up in region 2, then this is basically the same as thinking about Minkowski space in Rindler coordinates that you set up in region 1 and region 2. Okay, so that's the claim. Is that not clear, or if you? Well, the horizon is some global property. It's some global property of the space-time that divides so the black hole is some the horizon is it's not fair to really talk about the horizon as starting at some point, but it's some global property that divides the space-time into two regions, okay, which are causally disconnected. So the horizon is not a local object.
There is some point in time when observers realize they can't escape from a certain.
Well, observers never really realize that they can't escape. It's like saying that I realize that I can't escape beyond a light ray. And if the light ray crosses me, then I can never catch up with it. But there's no local experiment which observers can do to detect that they've crossed a horizon. We might have at this point of time just crossed a horizon. It could be that we have just crossed a horizon, or at least that's the semi-classical expectation. I'm going to spend this lecture trying to tell you why EMPS and others believe this is wrong. But the semi-classical expectation is we might just have crossed a horizon, and there's no way we will not now realize that we've crossed a horizon. There's no local experiment we can do. We are now inexorably falling towards a singularity, and nothing can save us from that fate. Okay, but we don't know that yet. Okay, there's no local experiment we can do, because to us it looks like we're in space. Okay, so there's no local thing that tells you that you've crossed the horizon. It's a global property. Okay, so some light ray just crossed us. This beam of light crossed me. I don't know. It could have been marking a horizon. But okay, are there any other questions about this?
Yeah, I have a confusion. An observer can realize an apparent horizon in that sense?
Can an observer realize that there's some apparent horizon that yeah, I don't see how locally you would determine that. It's okay. But if you're just sitting at one point, don't you just see, and you still have curvatures low at every point? How would you determine by look? So everything starts pointing in one direction. Um, okay, maybe. Okay. But if you're in a region of weak curvature everywhere again, and it's true that all geodesics start pointing inwards, but I mean you would need to trace them for some time. You'd need to go towards
very big black hole and you are falling
right.
the horizon, right?
Yeah.
So this could be an apparent horizon. You'd have to do some
You'd
one
have
over n
to-
experiments.
You'd have to go around the black hole. I think that much bigger you have to be probably.
Okay, you have to go around the black hole. Yeah.
But
If you explore the whole surface, yeah, then probably.
But you have to do some big. If you're in a big black hole, then it's very hard to detect an apparent horizon.
Not local.
Okay.
Locally you can.
Okay, not locally, but it doesn't depend on the future. It's not a.
Right, but you still have to do some. Experiment which involves yeah.
Yeah. Okay.
It's,
You
it's
have to
hard
go
to
around-
detect a local horizon. Yeah.
Go around the black.
Sorry, by apparent horizon,
I mean, just some point where all these geodesics start. Like what happens here. Everything starts. Yeah.
global horizon, some sort of an asymptote of an apparent horizon.
Well, the global horizon is some concept we talk about in terms of the global causal properties of the space time. And the apparent horizon is some property about how geodesics behave in some region. So you might be able to do so. Yeah.
Sir, the behavior of F at the horizon, which you discussed in the last lecture, that you wrote down more, is that because of this equivalence between the regular picture or this, or you?
This F has nothing to do with the Rindler picture.
No, as in the behavior of F hat at the horizon.
No, that just follows from the solution of the wave equation in the black.
At the using the semi-classical.
Yes, just the wave equation. Okay. Okay, so now the question is, if you want to write down this expansion behind, okay, you have to have, if it's really true that this is like Rindler, I'm kind of stating this as a fact, but it's true, then that means that you need some new modes behind the horizon. Okay, you need these modes BW behind the horizon so as to get a smooth two-point function across the horizon. Okay, so if you introduce another Schwarzschild patch, you can introduce another Schwarzschild patch in region 2. In this region, just like you introduce another Rindler patch in region 2, and in terms of this patch, it means what it means is that you have to write some other expansion into, let me call this G1, okay, plus O tilde omega k by root G tilde, okay, into G2 ZXT plus HC. Okay. So the claim I want to make, and I try to motivate this claim using Rindler, is that if you introduce a second Schwarzschild patch in region 2, then you try and write down a local expansion for the field in region 2, and then you make the same demand that the two-point function across this horizon is actually regular, which it should be because locally this horizon is indistinguishable from flat space. Then you find that you need not only these modes O omega k which you had here, but you also need these modes O tilde omega k. Okay, what are these functions G1 and G2? So G1 is roughly so both G1 and G2 solve the wave equation inside in region 2. Okay, they are solutions of the wave equation. G1 is the solution that matches up to F hat. Okay, so it's the analytic continuation of the left moving solution from region 1 to region 2. Whereas G2 is the other solution, it's the right moving solution inside region 2. Right, no boundary conditions at the horizon. So F hat actually consisted of both left and right moving solutions in this region, and G but F hat had some behavior near the horizon which consisted of left moving waves and right moving waves in terms of the horizon. You continue the left movers into region 2 and look at another solution of the wave equation. That's what I'm calling G1, okay, which is the and G hat G2 is the other right moving solution. Okay. Okay. If you like, I can say this in a little more detail. Okay, and the example of Rindler and higher dimensional Rindler. So I think Gautam will talk about two-dimensional Rindler, but if you want to discuss the example of higher dimensional Rindler, it's actually useful. So you can ask what are the solutions if you think of Rindler space minus dt squared plus dx squared plus dy squared. Okay, and if you try and write down the Rindler coordinates, which is that x minus t is equal to xr minus tr and x plus t e to the xr plus tr, and you ask for solutions of the wave equation box phi equal to 0, okay, the solution in this region 1, the regular solution, looks like e to the I omega tr e to the I k dot y. Okay, the modified Bessel function, the k Bessel function, I omega into k mod of k into e to the xr. Okay, and the normalization I happen to remember, I don't know why, is 1 by gamma of I omega. Okay, this is the solution in region 1. This is very similar to this f hat. Okay, so this k Bessel function in Rindler is the analog of the f hat. Okay, this is the solution in region 1. Then you can ask what are the solutions in region 2. Okay, there are two kinds of solutions in region 2. Okay, one solution is phi is equal to again e to the I omega tr e to the I k dot y. Okay, and then you have j of I omega into mod k e to the xr. Okay, that's one, and with the normalization I forget, it's gamma of 1 minus I omega roughly, but there's some normalization which I won't write down. Okay, and you have another solution which is e to the I omega tr into e to the I k dot y. Okay, which you can write, because this is not some integer, as jf minus I omega k of e to the xr. Okay, into some normalization which I'll just write as hash. Okay, so this is precisely the situation you have here also in the black hole is gone, but this is precisely a situation you have also in the black hole, that you have two solutions in region 2 and you have one kind of solution in region 1. Okay, and if you expand this solution near the boundary, which is this boundary here, okay, then you find that you get left movers and right movers that behave like e to the I omega into xr plus tr and e to the I omega into xr minus tr. Okay, and the same happens on this side. Okay, and here there's some particular phase shift, and the left movers here continue into some particular linear combination of this one and this one, and the right movers here are some independent guys which are multiplied by b, by the capital B mode. Okay, is this clear? Is what's happening clear?
XR goes to infinity then at the horizon, I guess?
XR goes to minus infinity, I think, in what I wrote. Yes, XR goes to minus infinity.
It's well behaved, I guess.
Yes, I think so. Yeah. It's going to 0. Yeah. Okay, so this is precisely the same situation here. Okay, and the key point is that you need a second independent set of modes which obey the properties as we discussed yesterday, which is that O tilde on omega k on the state of the CFT behaves like omega by 2 into O omega k dagger on psi. Okay, and this is a very important equation. Yeah.
You explained it yesterday, but this phi is in the region 1. So near the horizon, it has both left and right moving.
Right.
And in the region 2, you have left moving and right moving separately, right?
Yes.
And now which one goes to which one here? I mean, which one smoothly connects to it?
So that if you expand this out, there is one term that behaves like e to the I into xr plus whatever, e to the I omega into xr plus ky. Okay, and that is the one that connects smoothly to the part which looks like e to the I omega into xr plus tr. So the left movers from here connect smoothly to the left movers in region 2, and the right movers in region 2 are independent. They are the b omega, but they are independent, but they are entangled. Okay, and I want to emphasize that this is slightly different from the two-dimensional example that Gautam is explaining, because this k omega consists of both left movers and right movers. It's like a standing wave in region 1, which is exactly what we also have in AdS watcher.
The right movers here in the region 1?
There is, the left and the right movers are the same. This consists of both left and right movers. It's a standing wave. So there's no real difference between left and right movers. This K consists of both left and of right movers, which is the same as what happens in AdS. I mean, this Rindler, high dimensional Rindler creates a wall at large XR, just the same as AdS.
It seems to me, probably if you had a massive particle in 1 plus 1D Rindler, it might do something similar, right?
If you had a massive particle in 1 plus 1D,
Here along the y direction is like a mass for the
maybe, maybe.
equation.
Maybe we can, yeah, maybe it's, but I wouldn't watch for it on the fly. But it may be true. Yeah, we can discuss. Okay. Okay. So this being said, the claim is that you need these new degrees of freedom. Okay. This is one important claim I want to make. Okay. Here's another motivation to think of these new degrees of freedom, which is that think of there's what's called the Sena following geometry. Yeah, it'll come back. Okay, so there's what's called the eternal black hole geometry. Remember, just like you have a collapsing Schwarzschild black hole, you also have something called an eternal Schwarzschild black hole. You can think of the eternal black hole in anti-de Sitter space. This eternal black hole is a black hole, it's always existed. Okay, and this is its Penrose diagram. And Maldacena proposed in 2001, I think, that the dual of this eternal black hole is what's called the thermofield double state. Okay, so this eternal black hole has two boundaries. So the way you should think of it is as one CFT, another CFT, and the two are connected by a wormhole, as you see here. And Maldacena proposed in 2001 that the dual of this guy actually consisted of the following entangled state. Okay, which was an entangled state of the energy eigenstate in 1 with energy eigenstate in region 2. So this was the proposal, and there's some checks you can make of this proposal. Okay, and now the point is that this. Okay, so it's clear. There's this eternal black hole geometry you can write down anti-de Sitter space. The boundary of the eternal black hole consists of two CFTs. One conformal field theory living in one boundary, and another conformal field theory living on another boundary. Okay, and the proposal is that this eternal black hole is dual to a particular kind of entangled state, these two CFTs, which is the state entangled in this way, and this is what's called the thermofield double state for independent reasons in statistical mechanics. Okay, and now if you think of this eternal black hole, by the way, if you haven't seen this eternal black hole story, it's not critical to what I'm saying. It's just additional motivation if you'd like to hear it. But if you haven't seen this before, don't be scared. It's not going to be very important in what I'm going to say. Okay? That equation is important. The point is that this eternal black hole has some modes W that live here, also some modes W that live here. Okay, and if you just think of these modes O W and O tilde W in this state, you will see that they'll satisfy this equation. Okay, that O tilde W acting on psi does behave in fact like O omega dagger acting on psi. Okay, so you can check that for this particular entangled state, this is true. Okay, that the action of O tilde is like the action of O omega dagger on the state side. Okay, so this is the. Do you want me to show it in slightly more detail, or if you can work this out? I'm going to leave this as an exercise. Okay, you just take the state. Take a collection of harmonic oscillators that are made of modes of different frequencies omega, entangle them in a particular way. Okay, and check that if you act with one harmonic oscillator, okay, of from one side, that's the same as acting. The destruction operator on one side is the same as the creation operator on the other side. Okay, so try and verify this relation for this state while assuming that E is equal to sum of. Oh my God. So just imagine that you have a collection of harmonic oscillators, and the energy eigenstates are made by occupying all the oscillators with some occupancy NW. Just take this assumption and then verify. Okay, verify that it's a very simple exercise. That O tilde omega k on this psi TFD indeed equal to e to the minus beta w by 2 into O omega k dagger. Okay. Now the point about making this eternal black hole analogy is that the semi-classical expectation, okay, is also that if you think of a collapsing geometry, the collapsing geometry looks like the eternal black hole geometry at late times. If you take a collapsing geometry and you allow it to settle down, so that you're looking in that region P that I had pointed out that I erased, but which is hopefully in your notes. If you're looking at that region P, then this is the same at late times. The collapsing geometry, which is this geometry where you inserted something from some point in the bulb, and if you look at this geometry, then at late times the collapsing geometry goes over into the eternal black hole. Okay, semi-classical expectation, and the reason for that is simply that if you think of this point P, which remember is, I'm sorry, I'm not leaving enough space here, but I explained to you what this point P was. This point P, which is behind the horizon, and is living somewhere here far away from the matter, for this point P, it looks basically like you're in this region. The collapsing geometry approaches the eternal black hole at late times. And you can see that to construct, if you did this whole space-time construction in the eternal black hole geometry, and you asked what is the expansion of the fields in region 2, it's clear that you would get some expansion of this kind. Right, because you'd have modes that would come from this CFT and that would enter here, and you'd also have modes that would come from this CFT that would enter here. Okay? So if it is true that the semi-classical expectation that the collapsing geometry is the same as the eternal black hole is right, okay, then it's clear that you have to have this kind of an expansion with two different kinds of degrees of freedom, where the two different kinds of degrees of freedom are entangled in this particular way. Okay. Okay, so I've given you many different motivations for this. I'm just going to write down one critical formula which is going to be important for us. Maybe I can write it down here. Okay. There's a way to summarize all these expectations in terms of one formula. And the way to summarize these expectations in terms of one formula, is as follows, and that's the critical formula we are going to need. If you think of some correlation function of these two different degrees of freedom O and O tilde in the state psi. Okay. So let's say you think of some endpoint correlator. You put in O tilde of T1 prime up to O tilde of maybe you put in some more O's, O of T3, and you put in some O tilde of TL prime or TN prime, and then you put in some more O's, so you have O of TN. Okay, I put in too many O's, so okay, somewhere I should write OTN. Okay, let me just write OTN, O of T3, O of TN prime, O of Tn. Okay. Okay, so think of a correlation function. So remember I said that you had to have these different kinds of degrees of freedom O and these different kinds of degrees of freedom O tilde. Okay. Now I can take the O tildes and I can Fourier transform them back into something that depends on time. Okay, this O tilde of T is just a Fourier transform of these O tilde omega modes in time. Okay. Now you can think of some endpoint correlation function. Let me just try and explain the notation. So you insert some points. You insert the O's at some point T1 and at some point T2, okay. Then you insert some O tildes at some point T1 prime. Then you put another O which is at T3. Then you insert some more O tildes at some, up to some point Tn prime. And then you have some more O's all the way up to Tn, okay. So there's nothing deep here. I'm just inserting some O's and O tildes in random, okay. I'm putting some O's and some O tildes. The O tildes are at positions T1 prime, T2 prime up to Tn prime. And the O's are in positions T1, T2, T3 up to Tn. Okay, so I'm thinking of some correlation function which has n prime plus n points, okay, where these are in different positions. Okay, is this clear? Is this correlation function clear? Yeah, I'm just thinking of an endpoint correlation function. And the summary of all of this and the fact that the O tildes obey this equation and the fact that psi is close to a thermal state, okay, is the following, is that this correlation function must look like 1 by the partition function of the CFT, that's okay. No, it's just a product into trace of e to the minus beta h, okay. Now this is important, into O of T1 all the way up to O of Tn, where now there are no O tilde insertions, okay. And the O tilde insertions are now going to be reversed into O tilde of Tn prime, all the way up to O tilde of T1 prime, so Tn prime, plus I beta by 2, O tilde of T1 prime plus I beta by 2. Okay. Okay. So let me just say what I've done here. I'm claiming that there are two conditions you have to meet. One of them is that psi is close to a thermal state, and the second is that the O tildes have this behavior in Fourier space, and more precisely that the whole state looks like the thermophile double state, okay, which gives you other conditions also O tildes for higher point correlators. And the claim is that now if you think of some endpoint correlation function of the CFT in some state psi, that is the same as the thermal correlation function with the following things done. First, with all the O's moved to the left. Okay, so you pass all the O's through the O tildes and move them to the left. Second, you analytically continue the O tildes by I beta by 2, and you also reverse their relative ordering. Okay, so O tilde 1 came, T1 prime came first here, here it comes last. O tilde Tn prime came first here, here it comes first, it came last here, here it comes first, and all of them are analytically continued by a factor of I beta by 2, which is what enters here. Okay. So the claim is that the condition for a smooth horizon is this. Okay. So this is the central condition for a smooth horizon. Okay, I haven't dotted all the I's and crossed all the T's, but if you Fourier transform this and if you think in more detail about how you set up the equivalence with the eternal black hole, you will find this condition. Okay. Now this is the condition I'm going to use. Yes.
That condition for smooth horizon, or is it saying that if that in the eternal black hole case, this would be the condition met and the geometry settles down to being close to the eternal black hole?
So when the geometry settles down to being close to the eternal black hole, which is what you expect in a semi-classical thing, then you would need these new degrees of freedom behind the black hole, and those new degrees of freedom need to satisfy this in order to get a smooth 2-point function across. So from the smoothness of 2-point function, yes, you can derive this, and I was trying to give you another derivation of this, which is also from the eternal black hole. You also expect in the eternal black hole. But just from the smoothness of the 2-point function, as I was trying to argue yesterday, you need this relation between the modes, and if you transform this in Fourier space and put it into an endpoint correlation function, this I beta by 2 is here to give you these factors of e to the minus beta w, okay, and you just Fourier transform it and put it together, you get this relation. Okay, yeah.
Commute?
Yeah, so the O tildes commute with the O's. So why do the O tildes commute with the O's?
Why don't they commute with each other?
Why don't they commute with each other?
Yeah, because O tilde doesn't commute with O tilde dagger, right? But there are no O tilde daggers here at all.
No, so this is O tilde of t. So O of t doesn't, there may also be some x positions here. So O of t doesn't commute with necessarily O of t itself. If one is in the forward cone of the other, it may be different. It may have some non-trivial commutator. Okay. So these operators in general, the O's don't commute with each other and the O tildes don't commute with each other. Okay, they don't commute with each other. However, it's true the O's and the O tildes commute. And not only do the O tildes commute, they also have this funny behavior in that their relative ordering gets reversed. Okay, so this is the condition for there to be a smooth horizon. Okay, so I've tried to motivate in various ways. I've tried to motivate it, and I can write down this condition in momentum space as well. Let me write that down, and I'll just keep this board. Okay, the analogous condition in momentum space, if you just Fourier transform this, is just that you can think of this as two conditions. First, that psi of O of omega 1 k1 into O of omega n kn is equal to trace of e to the minus beta h into this guy, which is just a statement that psi is a typical thermal state. And you can think of it secondly, and just writing the same condition in 2 steps in momentum space, omega 1 k1 into some O tilde of omega 1 k1, omega 1 prime k1 prime, O of omega n kn, tilde of omega n prime kn prime, okay, is equal to psi of 1 k1 all the way up to n kn, okay, and these orderings reversed again. So with O omega n prime kn prime dagger omega 1 prime k1 prime. I'm sorry if you can't see the primes on top, okay, but all the O tildes have a primes. If you can't see the primes at the back, okay, all the O tildes have a prime sitting there. Psi into e to the minus beta omega 1 prime all the way up to omega n prime by 2. Okay, So this relation we already saw how the O tilde act like O omega dagger. Okay. So what I'm saying is if you put this together in an endpoint function, the claim is again that you think of some product of operators like this, and the same thing happens. You know, the relative ordering of the O tildes gets reversed. They turn into ordinary operators but with a dagger on top. Okay. The relative ordering gets reversed and they pick up these e to the minus beta factors, and this is the same condition in position space. Okay. So this board is summarizing for you the conditions for there to be a smooth horizon in the CFT. If I can find operators that satisfy this relation, then this gives me a smooth horizon in the CFT. Okay, then I can construct for you these local operators that obey all the right conditions and that have the smooth horizon in the CFT. Okay. And you can see here that these operators O tilde have to do some magic. They have to commute through the O's. Okay. And that's a strong kind of statement. You know, you have to find some operators that commute through the O's and automatically, you know, reverse their ordering. So the operators somehow acting on a generic state have to have this property. Okay, so is this statement clear? This is the claim. Okay, and I try to motivate the claim by looking at Rindler and the eternal black hole and so on, but in the end that's the claim. Okay, is the claim at least clear? Today it looks like I'm losing people because I'm getting less questions, so I'm happy to take questions here. Yeah.
How do I see that O and O tilde as commute?
How do you see that O and O tilde as commute? No. See, so the claim is just that, you know, if you think of the, so there are various ways to see it. You know, if you think of the eternal black hole here, for example, the O's and O tildes they commute. Okay? If you think of the eternal black hole here, O belongs to one CFT and O tilde belongs to the other CFT. So if you ask for some correlation function where the O's are inserted and some O tildes are inserted, you know, it has this property. And similarly, you can try and ask for, you know, the condition for various correlators to be smooth across the horizon, and those correlators will not be smooth and will not obey the properties of local field theories unless the O's and O tildes commute. So the condition that the O's and O tildes commute was the condition we had in Rindler, which was the capital B that I wrote yesterday, and small a commutator was 0. Now this was the condition that this capital B commuted with a small a living here, that these B's and these A's were independent degrees of freedom. Okay, so this condition that O's and O tildes commute is the same as the condition in Rindler that the capital B and the small a commute. And then the second condition, which is that the O tildes first they commute, but second they start acting like O of ordinary dagger, is this condition for the smoothness that we had. Okay, so that's where these two conditions come from. So I'm giving you two motivations. Okay, in Rindler you could see that these B's commute with the small a's, and in the eternal black hole you can see these guys are coming from the other side. In fact, that's the same reason in Rindler. These B's are really coming from this region 3. So there are some independent degrees of freedom. There are some right movers that are coming from region 3. Okay, so yeah.
I'm not so sure about this. Where is the second condition coming from?
This condition?
Yeah.
So this condition is coming from, you know, the statement that O tilde acts like an O dagger. So if you start with this O tilde here, this acts like an O dagger. Okay. Now you have some other O tildes. Because the O tildes commute with the psi, you pass them to the right, and then they act like an O dagger again. So if you keep imposing this condition that the O tildes commute with the O's, and when they act on psi, they act like an O dagger, you'll get this, you'll get the reversal, and you'll also get all these factors. Okay. So the central condition was what I wrote before erasing this, which was that O tilde acting on psi was the same as O dagger acting on psi, and that the O tildes commute with the O's. If you use those conditions repeatedly, you'll get this condition for an endpoint function.
There, what has happened?
So the
omega n prime pn prime has moved to the left.
To the left.
Because they commute.
Because they commute. It's moved. It's always to the right of all the O's, but it's moved to the left of all the others. You know, first you move all the O tildes to the right of all the O's. Then you start acting, you know, one by one. So first you have to act with this guy. You after that, then you move it, pull it back. So it's sitting, you know, just to the right of the last of these guys, and you keep doing that.
Thank you.
What class of state psi, what precise class of state psi is it for which this is?
That's the question of what class of states psi obey this relation 1 that I approximately thermal. I would say a generic state at high energies of order n squared obeys this condition. So a generic state obeys this condition. In fact, you can try and make this a little more precise. I'll try and make it a little more precise. You want a generic state at high energies, which is a state which is in equilibrium where correlation functions are time translationally invaded. And then I think, you know, that should generally be enough to guarantee that correlators at leading order in 1 by n, not of course at all orders, but at leading order in 1 by n look like thermal correlators. So an energy eigenstate, for example, should satisfy this condition.
I'm a little confused, probably this is something silly. If I took a psi and then another psi prime, which is just 4 times psi.
Yes.
psi prime, I would write the same thing.
So psi prime is then not an equilibrium state. So psi prime is an excitation of some equilibrium state by O.
But it's by a very tiny.
So that's right. So it would, this relation would also be modified by a small amount, which would be up to the insertion of your O prime.
But when you said generic order n square state, you would be sensitive.
Yes, generic order n square state, which is also an equilibrium. So generic where correlators are time translationally invariant. If you insert your O omega on them, then that correlator I think is not time translationally. You've made some insertion of something with some frequency.
But with only 1 over n square.
Right. So this would also get corrected in that limit only in some subleading order only. But for example, if you put O omega on psi prime and you try to ask for the expectation value of the same number operator corresponding to that frequency, that would give you a leading order correction. For every other frequency, it would be a small correction. So you can detect that there's something which is non-thermal about that state by measuring the occupancy of modes in that state, and that's not the Bose-Einstein occupancy, it's the Bose-Einstein occupancy plus 1. So there's something which is different about that state, which is not an equilibrium.
But it would be small.
So for that mode, it would not be small. The overall correction to the state would be small because there are many modes. But if you take one frequency and you insert one more oscillator of that frequency, or you remove one oscillator from that frequency, then by measuring the number operator for that particular mode, you can see the occupancy is not e to the minus beta by 1 minus e to the minus beta, but it's that plus 1. So you can detect it by measuring things.
It's a fine measurement, yeah.
It's a fine measurement, right? So it's a fine measurement, yeah.
So, on the mixer in the collapsing geometry, so where exactly you are inserting O and O tilde?
Where you inserting O and O tilde? These are on the boundary. These are boundary insertions.
Are we talking in the eternal black hole language or what language are we talking?
So these are boundary insertions in a single boundary, on the same boundary. So in the end, I want to talk about a collapsing geometry. I'm always talking about a collapsing geometry, 1 CFT. I introduced the eternal black hole only as an analogy to say that the collapsing geometry looks like the eternal black hole at late times. Okay. Now the claim is that in a single CFT, you have to find me these degrees of freedom that have this problem. And then you get a slope.
So from this, so O tilde mode, I mean the O tilde mode you wanted to identify with BW, right?
Right.
And BW are the mode which matches to AW smoothly?
No, BWs are the modes that come from the other side.
So so suppose I have only one-sided CFT. I mean, how do I understand?
That's the question. How do you get them? You need them. So you need them to get a smooth horizon. So where do you get them in the single CFT? So we have to try and find them. If you can't find them, then the Mathur and Butchinsky and others are right. And then there's a firewall. So if you can't find them, then there's a firewall. Otherwise, you have to find them somewhere, or there's a firewall.
What's the analogy of the thermophile double state in this particular single-sided CFT?
So the analogy is just that these O tildes behave like insertions on the other side. In a single CFT, these O tilde, at least in momentum space is clear to think about, but you don't have to worry about which side.
No, the state. It has to be what kind of a state? In case of over there, you create the state by taking two ideal states of energies from two of the different CFT. In case of a single CFT.
So in case of a single CFT, you just take some highly energetic state, and the claim is that the highly energetic state should look like the thermophile double state after you've allowed it to equilibrate. So in particular, as part of looking at the thermophile double state, it also should have this effective doubling of the number of degrees of freedom.
Is there a restriction on how big little n can be for the first condition to
Right. So certainly you don't want little n to start scaling like the central charge of the theory. If it starts scaling like that, then in general, all of these expectations fail. You don't expect correlators to occur. So little n and little n prime shouldn't scale like n squared, the capital N squared. What am I doing for time? Half an hour?
No, 15 minutes, but of course you can take a little more time.
I'll take a little more time. Yes. That's too bad. Yeah.
When you discussed it yesterday,
Yeah.
you argued that we need some doubling of modes and we need to find these O tilde modes, and the only restrictions on these O tilde modes were that from the smoothness of the horizon, O tilde has to be like O dagger.
Right.
But somehow it seems that you have translated that restrictions to these correlation functions, where you have added this extra information that the states on which they act should be like thermal.
That's an information you need anyway, even for something outside the black hole horizon to work. And anyway, if the geometry is to look like a black hole geometry, it better be the state that the state in which you're working is close to a thermal state. So that is some information which is additional. That's not relevant to the horizon itself. This condition you need even for states, even for just insertions of the ordinary O's, that things should look like things should look thermal. So you're working in a highly excited state in which things look thermal.
So when added these two conditions added gives me these restrictions, right?
This gives me the first restriction. Yes, I wrote the first restriction in 2 steps at the bottom. Okay, I'm doing very badly for time, so I'm going to now actually talk about why O tildes don't exist. Okay, and tomorrow I'll construct them. I thought I had 15 minutes behind schedule. Let me now talk about some recent progress by Mathur and AMPS. Okay, claim. This is the claim in my language. This is the claim paraphrased. Okay, claim O tilde omega do not exist in a single CFT. And a firewall and a fuzzball, depending on who you're talking to. Okay, so the claim is, and I'm now going to try and make this claim in the next 20 minutes, that O tilde omega do not exist in a single CFT. You can't find these operators in a single CFT. You can't find operators that meet this condition. So there's no smooth horizon, and actually there's a firewall or a fuzzball. Okay, that's the claim of Mathur and AMPS. Very recent. This is from 2009, and this is all from 2012 to 13. And as many of you know, there's been a lot of recent activity on this work. And really the claim is the claim about the existence of these operators O tilde. I think everything can be phrased in that language. Okay? So let me tell you the 4 claims that suggest that this is the case. Okay? And so there are roughly 4 claims that do this. And they are there's what's called the strong subadditivity paradox. Or maybe 3 claims, and I'll discuss one tomorrow because it's related to resolution of this. Let me tell you about 3 right now. Okay, there's what's called the strong subadditivity paradox, which I'll describe. There's what's called the lack of a left paradox. Okay. And there's what's called the n alpha not equal to 0 paradox. Okay. Usually people talk about the strong subadditivity paradox. Let me start by, and perhaps some of you have seen it before. Can I get a sense of how many of you might have seen the strong subadditivity paradox? Just a rough sense of how many would have seen it. If you can. Oh, not too many. Oh, that's true. Okay. Okay, fine. But nevertheless, the strong subadditivity paradox is a little hard to understand. So I'm going to start with 2. Okay, I'll first describe for you why this is a claim just by AMPSS actually. Okay, so AMPSS, which is Almeri, Marolf, Polchinski, Sully, and Stanford. Okay, so AMPSS, and the claim is that you can't have these O tilde omega operators because there's a lack of a because you left inverse. What does that mean? That means the following. Think of these O tilde omega operators. Okay? So remember I said that the O tilde omega operators act like O dagger, and related to that is the relation that the O tilde omega dagger operators, okay, the operators that create the particle behind the horizon, they act in some way like this. The sign reverses. Okay. Okay, so that suggests that if you think of the CFT Hamiltonian, okay, then H into O tilde omega dagger is equal to minus omega into O tilde omega dagger. Okay. That means that O tilde omega dagger lowers the energy of a state, okay, which is true because we demanded that O tilde omega dagger acts like O omega, and O omega lowers the energy of a state. That means that the claim is that the Hamiltonian commuting with this gives you minus omega into omega dagger. Okay, is this clear? This is something very simple. Because O tilde omega, the horizon is like creating something of negative energy. Okay. There are various ways to understand this. One way to understand this also very colloquially, although what I said written there is more precise, is if you think of this, if you think of the Schwarzschild geometry, then in some sense particles that you create behind the horizon have negative energy. That's how Hawking pair production can happen. Because you eject something with positive energy and there's something which has negative energy in some sense with respect to Schwarzschild time that's ejected inside. Okay? That's the intuitive way of understanding this, but the precise way is that we found an equation. We said O tilde omega looks like O omega on psi. So since O omega reduces the energy, it better be the case that O tilde omega dagger, also has this kind of commutator with the CFT Hamiltonian, where H is the CFT Hamiltonian. But it looks like we're in trouble because we also have a commutation relation, which is that O omega, okay, O tilde omega dagger is equal to 1. And this better be the case if our quantization of the field and so on is to make sense. Now these O tilde, is equal to G omega. So sorry, let me just define some new modes. Okay, let me call A tilde omega is equal to O tilde omega divided by root of G omega. Okay? Where G omega was the commutator. G omega is completely unimportant for what we have to say here, but I'm just defining this, so I'll write A here. Okay. Now really this is A tilde omega prime, and A omega is equal to delta of omega minus omega prime. And if you want me to do this more carefully, I have to make wave packets that are sharply peaked about something that integrate to 1. But I hope it's okay if I write colloquially right now that A tilde omega into A tilde omega dagger is equal to 1. Okay. So yesterday I described them in a delta function normalization. They are described in that way, but you can still constructing small wave packets. I hope I don't have to do that. Is this clear? Is everyone happy with this? This is just a statement of canonical commutation relation. Okay, but if you think of this statement, then it looks A tilde into A tilde omega dagger, okay, is equal to 1 plus A tilde omega dagger omega. Okay, I haven't done anything. I just wrote this expansion out. Okay, but it means that A tilde omega into A tilde omega into the inverse of that guy is equal to 1. Okay, this guy is invertible because this is a positive operator. So this 1 plus A tilde omega into A tilde, A dagger into A is invertible. So I multiplied by the inverse from the left side. So I have A. So this is true, right? So far I have just recast this whole equation in this way. But that means that this operator has a left inverse. Okay. Is everyone happy with this? Okay. By the way, if you haven't been following anything I said so far, forget about that. This is just a statement about simple harmonic oscillators. Okay, if you think of the creation operator in simple harmonic oscillators, the creation operator has a left inverse. I just did the algebra to write down what the left inverse is. Is everyone happy with this? Okay. But how can A tilde omega dagger have a left inverse? Because it also has negative energy. Usually the creation operator has positive energy. But look here, it has negative energy, and the CFT, so CFT states, number of CFT states grows monotonically with E, with energy, right? So there are fewer states, just a second. So there are fewer states at lower energy than there are at higher energy. Okay? But O tilde omega dagger maps a state of higher energy to a state of lower energy, and it has left inverse. Okay? How can that be? Because there are fewer states at lower energy than there are at higher energy. So there's no invertible mapping. There's no mapping which has a left inverse which does this. Okay? No map with a left inverse can map E to E minus omega, which is what O tilde omega seems to be doing. Okay. By the way, I should say that I'm presenting the AMPSS arguments, without comment here. I think all of these arguments have subtleties and they're kind of incorrect, I think, or they're counter arguments to all of these. But I'm just presenting them to you without bias because I think they're interesting arguments and they're worth thinking about. Okay? Hence, O tilde omega dagger doesn't exist. Okay, there is no operator that has this property. There's no operator that has simultaneously this property, and both of which we wanted. Okay? This is the lack of a left inverse argument. You had a question, someone had a question, yeah. This statement? No. So I took this and then I multiplied it by the inverse of 1 plus A tilde omega into M. This is the left inverse of A tilde omega dagger. Yeah. This side is invertible because this is a positive operator.
Okay.
This is 1. It's 1 plus positive.
And also, where do you get that statement from? The numbers statement.
This is a well-known statement about the CFT. This is just a statement about specific heats and so on. How does the entropy grow with energy? Entropy increases with energy. So almost every thermodynamic system has it.
So
Except for black. Yeah.
Here you said so there A tilde dagger.
These two things look the same, but this is a 1, this is a, yeah.
A tilde dagger has a left inverse, so here what exactly is the argument? Sorry, I did not follow.
So A tilde dagger has a left inverse, but A tilde dagger can't have a left inverse. Because it lowers the energy, and no state to the low energy can have a left inverse. No operator that lowers the energy that takes e to e minus omega can have a left inverse. Because the number of states at higher energy is more than the number of states at lower energy. So this is called the counting argument, the lack of a left inverse paradox, and it's kind of it's one of the key arguments. In fact, it's in some sense it's the best posed argument of this whole set of arguments. It's simplest and most straightforward to state. Okay, let me now describe in some other order the so-called n alpha not equal to 0. Well, maybe I'll describe strong subadditivity. How am I doing for time again? Sorry. Do I have 15 minutes more or not really? I don't really. 10 minutes more? Okay, I'll try and. Okay, let me give you the strong. Okay. So the idea in thinking of the strong subadditivity paradox is to think of some operators, is to think of a black hole, okay, and allow the black hole to evaporate. So you start with some black hole, okay, and after some time the black hole evaporates. And the way it evaporates is that it emits some of these quanta that are created by O omega, okay, and it emits some other quanta that are created by O tilde omega. Okay. So let me call the quanta that fall inside C and the quanta that fall outside B. Okay. And let me call the collection of all the emitted quanta E. So there are 3 subsystems. A is the old radiation. Okay. B is quanta just being emitted. Okay. And C is outside. So this is emitted by the OWs. Okay. And C is quanta inside. So this is an excitation of OW dagger. This is an excitation of OW tilde dagger. Okay. I should say that everything I was doing here was really for big black holes that don't really evaporate. And if you like, in the discussion session, I can try and tell you how to make big black holes evaporate. The way you want to make big black holes evaporate is really by turning on some coupling of the CFT to some other theory. Because you turn on wire that links the CFT to some other theory, and that absorbs some energy. Okay, so that can cause a big black hole in antidistant space to evaporate. Okay, if you want to think precisely about how these things evaporate, but if not, and you're happy to think colloquially, then let's just think colloquially, and which is how I'll describe this paradox, and I can try and make it more precise for you if you like in the discussion session. So think of three subsystems. A is a set of old radiation. You have a black hole that's emitting, it has some old radiation. B is a quanta that's just being emitted, so the black hole is radiating via pair creation, and C is the quanta which is being emitted inside. Okay, so at every step the black hole is emitting pairs of particles created by O omega and O tilde omega dagger, and there are many such particles which have been emitted, and those are the old radiation. Okay, so there are these three subsystems. Now we need the following conditions. Okay, we need the following conditions. First, think of the entanglement entropy of the old radiation. Okay, which is the entanglement entropy of the old radiation that you've seen recently. How does this entanglement entropy behave? So it starts at 0. The reason it starts at 0 is that in the beginning there is no old radiation, there's no radiation outside. So it just starts at 0. Okay. It goes up because more and more radiation starts being emitted. This radiation is all thermal. You collect some thermal particles, they have some entropy that adds up. Okay. But in the end, if the black hole is pure, it has to go down. Okay, because in the end, the state is pure. So you start with a pure state, you allow it to collapse, and then you allow the pure state to evaporate. Okay. When the pure state evaporates, and if you think of the entropy of the radiation that's being emitted, in the beginning it goes up, in the end it comes down. In fact, there are some general arguments by Page, okay, Page, and the paper is called the average entropy of a subsystem. Tell you that this curve has to behave like this. It has a sharp turnaround and it comes around like this, and this time is called the Page time. Okay. So this is the entropy of SA versus time. Assuming information is not lost. This is assuming you started with a pure state and that information was not lost. Okay. So if information is not lost, then you have this. Okay. Now let's be on this part of the curve. Okay, somewhere here after the Page time. Okay. Now what are the things I know? The things I know are that A, this B is going to go and join A. Okay, this B is going to go and join A. And that's just a statement that I'm on this part of the curve. So I know that SAB is smaller than SA. That's the statement that after some time, A of T plus delta T is equal to A of T. Remember, because B is the particle that's just being emitted. If I think of A after some time, that's the A at some time, union the B at the same time. So this is a statement that SAB is smaller than SA. It will also be smaller than SB. So SB is No. So SAB is smaller than SA. SAB is not necessarily smaller than SB. SAB can be some very large number. SB is something just one bit.
Okay, because B is just one single.
B is one. So B is going to purify.
Yeah, sorry.
Again, we need SBC equal to 0. This is the statement that B and C have the same information. Okay, really this equation we've been writing many times, which is that O tilde omega is the same as O omega dagger acting on the state psi, is telling you that O and O tilde in some sense contain the same information. This is the statement of entanglement. Okay, that the modes outside and the modes inside are entangled. I can try and make this more precise for you if you like, but as you can see, this paradox is not phrased in terms of correlation functions the way we are phrasing it. But I can try and make it more precise if you like in the discussion. Okay. But for now, the statement we've been making repeatedly that O tilde is the action on O tilde on the state psi is the same as the action of O omega dagger on psi, can be understood to be the statement that the modes outside and the modes inside are entangled, which is the statement that SBC is equal to 0. Okay. But remember also that if you just think of if you think of one of these Hawking quanta that are being emitted, or if you think of one particular mode. Remember we discussed yesterday how the occupancy of this mode was thermal. Okay, so this mode has some thermal distribution in its occupancy, and that is the statement that SB equal to SC is greater than 0. which is that each individual Hawking quanta that's being emitted has a positive entropy. But these three statements are in contradiction with the strong subadditivity of entropy that Tadashi told you about yesterday, which is that SAB plus SBC, okay, is greater than or equal to SA plus SC, which clearly looks like it's being violated. Okay, because SAB is smaller than SA and SBC is 0 and SC is some positive number. So strong subadditivity of entropy violated. You're right, SSA is the short form, right? For some reason, strong subadditivity. Strong subadditivity. It's not violated by some order 1 corrections, it's violated by this big SC. Okay. That's another reason they say that hence you have to give up the statement that SBC is 0, and this is what creates a firewall. Okay. Let me just take a step back and remind you. You start with this big black hole. The fact that information is not lost tells you that SAB is smaller than SA after some time. This is the statement of unitarity. SBC is equal to 0 is a statement we've been discussing for the past some time, which is that the modes inside are entangled with the modes outside. Okay. SB is equal to SC is greater than 0 is simply the statement that Hawking radiation is thermal, which also we've been tacitly discussing. Okay. So you have these three statements, and these three statements look like they're in contradiction with the strong subadditivity of entropy by some order 1 amount, because this is violated by by some significant amount. SC is some order 1 number. Okay. And so that looks like so it looks like you're in trouble. It's not something that can be fixed by small corrections. Okay. This is the second argument, the strong subadditivity of entropy argument, that suggests that hence you should give up this notion that the inside modes are entangled with the outside modes, give up the notion that SBC is 0, so to satisfy the strong subadditivity of entropy. When you give up this notion, you give up the idea of a smooth horizon, as we've discussed many times. So you don't have a smooth horizon if the modes inside are not entangled. Okay, let me give you the third and last argument and I'll stop. Third and last argument is roughly the following argument. Okay, this is a good way to understand. The third and last argument is just by Marolf and Polchinski. It's a paper that's just by them, a small paper, 5 paper, and the argument is as follows. You see, think of the mode as seen by the infalling observer, okay, and right. So the infalling observer, the condition for the infalling observer to see a smooth horizon is that first of all that EW on psi, EW dagger into minus beta omega by 2 psi, okay. And similarly tilde on psi. Okay. So these are the conditions that the infalling observer should see a smooth horizon. Now you can ask, why are these conditions satisfied if you think of Rindler space? If you think of the Minkowski geometry in terms of Rindler space, you can ask, why is it that the modes at the left and the right satisfy this condition between these modes A and A tilde? Okay? The reason they satisfy this is because there's an energetic condition. If you think of the Minkowski Hamiltonian and you think of states, so this is a condition for the states. Right? If you think of states that don't satisfy this condition, then in those states in Minkowski space, states that don't satisfy this then it has very high energy. Okay. Is large. Okay, the Minkowski energy. Okay, so this is true, you can check. Okay. But in the CFT, the CFT Hamiltonian, which is the Schwarzschild, it's like the Hamiltonian for the asymptotic Schwarzschild time, is in fact like the Rindler Hamiltonian. Okay. So HC is like Rindler Hamiltonian. Okay. Hence, there is no energetic reason that these conditions should be satisfied. Okay. because there's no reason that tells you if this condition is not satisfied, the energy of the state will be very large. So you give me some operator A tilde, because the Hamiltonian of the CFT is Hamiltonian, there's no energetic reason, and hence, if you give me some state for which this is satisfied, I can give you some other state for which this is not satisfied. Now, in fact, for a generic state of energy E, if you impose some operator relation like this, that restricts you to a measure 0 set of states. So, in fact, for most states, for a generic state, this condition is not met because there's no energetic reason to meet this condition. Okay. So, as a result, because AdS CFT is like the Rindler Hamiltonian, this condition is not met. This condition, this focuses you. The claim is that this focuses on that's right. No, there's something stronger than that. In fact, if you think of states that are slightly excited about the Minkowski vacuum, they in fact do obey this condition still for to an excellent approximation. So if you really start violating this condition for all sorts of modes, then that's some state of some very high energy. Yes, yes, and then that will be a firewall state. From the Minkowski, right. So if you take some arbitrary state in Rindler on the left and arbitrary state on the right and you glue them together, you get a firewall in Minkowski space. So if you did that process, then the generic state you would get in Minkowski space is a firewall. Now the reason you say that Minkowski space doesn't have a firewall is you say, we are living at finite energy. We have only finite energy excitation.
I mean, who knows?
Well, okay.
The reason I say this, you don't say it for energy reasons. You say, I know what I started with. I started with the Minkowski vacuum and something falling in.
Yes.
And what I get is the undrew vacuum.
Okay. So
it's
what,
not because of energetic reasons.
Right. So what these people say is, why don't you compute? They'll say you compute trace in the microcanonical ensemble of n alpha, where n alpha is the occupancy as measured by the infalling observer, which is actually made of creation operators of this kind, A omega minus this kind. So measure trace in the microcanonical ensemble. Okay. And in fact, to evaluate this trace, they say go to a, so I'll just take 1 minute more, then I'm done. Okay. So just one minute. So since you asked me a question, I'll take that advantage to give 1 minute more, and then I'm done. Okay. So they say that think of the number operator NW. Okay, so NW and H is approximately 0. Okay, plus order 1 by n. This is just a statement in the CFT. Okay. Now compute trace of e to the minus, compute this trace of n alpha, okay, in the microcanonical ensemble. Instead of computing it in the energy eigenbasis, change the basis to go to a number eigenbasis of NW. Okay. N alpha so n alpha is alpha dagger alpha, where alpha is that combination. So alpha is equal to this combination, minus e to the minus beta w by 2 into a tilde omega dagger, and plus so alpha 1 dagger alpha 1, alpha 2 dagger alpha 2, alpha 1 is this and alpha 2 is the other combination. N alpha is a number operator as seen by the infalling observer. It's what you get by doing the Bogoliubov transform to the infalling observer's frame and asking what are the creation annihilation operators the infalling observer sees. The infalling observer sees two kinds of creation annihilation operators. One of them is just related to the the ordinary Rindler operators or the Schwarzschild operators by this Bogoliubov transform, and then the other one is related in this other way by a tilde omega minus this. Okay, and so n alpha is a number operator. Is that good? Okay. So they say you want to compute trace of n alpha over some finite energy in the microcanonical ensemble, and because n omega and h are approximately they commute, hence you can instead compute this trace in an n omega basis, in a basis of number eigenstates. Now this you can't do in the Rindler case. In Rindler and Minkowski, if you want to compute the trace of n alpha over in the microcanonical ensemble, you can't go over to a base of n omega eigenstates because all these n omega eigenstates have infinite energy. But that's not true here. The n omega eigenstates don't have infinite energy. Okay? And n alpha is a positive operator. So there's no possibility of any cancellations. Okay, and in each n omega eigenstate, expectation value of n alpha is positive, and as a result, this trace is positive. Okay. And so the number operator as seen by an infalling observer has a positive expectation value. Okay. And the key physics here, the key physical point is that the CFT Hamiltonian looks like the Rindler Hamiltonian, and if you took Rindler space and tried to compute in a Rindler microcanonical ensemble, not in the Minkowski microcanonical ensemble, but in the Rindler microcanonical ensemble, the trace of the number operator as seen by the Minkowski observer, that indeed would be a non-zero number. And so the claim is that the trace in the CFT microcanonical ensemble is like the trace in the Rindler microcanonical ensemble, and that's a positive number. Okay, I'm probably way beyond time, so I'll stop here and we can have more in the discussion.
Okay, Rajesh.
Yes.
Is there an immediate objection to the fact that it treated the H commutator of H with this O tilde as an operator equation? But that's nowhere near being true, right?
Right. So indeed, you can try and get around that. Although I can give you a little bit of a defense of that. It's true that you don't have to treat it exactly as an operator equation, except if you're in an energy eigenstate. You see, if you're in an energy eigenstate, then the fact that A omega match takes you from an energy eigenstate E to E minus omega, really tells you that omega minus A omega at least as acting on the state psi. You're right, at least as acting on the state psi tells you that H omega has to be minus omega. It is true that H omega lowers the expectation value, acting with this omega lowers the expectation value of the energy. So it takes you from some ensemble with some spread to something with a lower expectation value. Actually, you might try and find a solution by trying to get around that and trying to say, that there are some edge effects and maybe the width increases in something. So that is a possible solution that, you don't have to impose this as an operator equation. You can try and get around it in some way. So that is a possible solution actually. I think that's actually quite an interesting, I think that's an interesting thread to follow about whether, you don't have to impose that as an operator equation and whether you can try and get around it in some way by, getting around the fact that there are lower states at lower energy by increasing the spread of energies or something. I think that's an interesting thread to follow. So, let me say one thing just as a caveat. All of these arguments have loopholes. Okay, in fact, I'm going to spend all of tomorrow trying to tell you ways around these arguments and why there's no firewall. Okay, none of these arguments are very rigorously phrased, and as Rajesh just pointed out, there are many tacit assumptions and things that you do here. Okay, but these arguments are nevertheless suggestive and interesting. Okay, so it's interesting to think about them, but they all have loopholes, and none of them are proofs, as indeed they shouldn't be.
Okay, well, let's thank Suvrat again. And